So I'd like to finish the problem that we didn't get to today in class. So we had talked in class how you can reduce an alkyne to the alkane, or you can stop at the cis-alkene using a poisoned palladium catalyst called Lindlar's catalyst. And so I had mentioned that we can also reduce to a transalkene, and that reaction is shown up here, and that is known as a dissolving metal reduction. You do not have to know the mechanism of this. What was key is that lithium is your metal, and lithium is in the zero oxidation state. And so what happens is it loses an electron and it becomes lithium plus. And this electron is what's added to the molecule, and that reduces your alkene, causing a trans arrangement of the electron and the two electron pair, which results in your transalkene. So you should know that if you have an alkyne plus dissolving metal conditions, you'll get the transalkene, and the solvent here is going to be an amine or ammonia, just NH3. And then on the following slide, we had some practice problems that I would like to go through. So it says what product is formed in each, and so you have 3 sets of reactions on that page. I'm going to start with the top one, and then we'll do the bottom one, and then the middle. Okay. So in the top, we have an alkene, and we react it with H2 and palladium. This is a hydrogenation reaction. And hydrogenation of alkenes equal the alkane, and you get the cis arrangement. And so you draw the backbone the same, but now you have cis arrangement of the hydrogens. We also have to name this molecule, and this is a bicyclo molecule. And we learned how to name that in chapter 4. It's a fused ring system, and when we name these, we put the word bicyclo out front, and then in parentheses, we put the numbers, so 1, 2, 3, 1, 2, 3, and 0. So this is 3, 3, 0. That told us it was fused because of the 0. And then the final name is the total number of carbons. So 1, 2, 3, 4, 5, 6, 7, 8 octane. Remember that the sum of the numbers inside the brackets is always 2 less than the total number because of the bridgeheads. And then we want to put the name cis out front. This molecule actually has no chiral centers. This is not a stereocenter because you never hit a point of difference, and because you have symmetry in 2 different ways through this molecule. So let me erase this problem so that we have room to work on the last problem. So in the last problem, you are given an alcohol and then 2 steps right in a row, written together. And my advice on these is to just draw the first step first and draw the product that results. Okay, so we have an alcohol, and then we have NaH. This stood for sodium hydride. And so sodium hydride has H minus, which is a base, and it can deprotonate this hydrogen. And so that forms the O minus, and then H2 is a byproduct, and then we have this sodium. And this might look a little weird, but this is basically terbutoxide. We know terbutoxide because this was a bulky base. In the second step, it tells us a name, 2-bromo, 2-methylbutane. And so we should draw that. So butane, 2-bromo, 2-methyl butane. And it's asking to predict the product. So the types of reactions we've learned are acid-base. We have substitution, and we have elimination. Okay? Even though this is a base, this is not an acid, and so we can rule out acid-base. And so we ask ourselves, is this a substitution or elimination? In this case, you want to use your flow chart. And in the flow chart, we have our nucleophile is a good nucleophile because it's O-, but it's bulky. So it's a good nucleophile, but it's bulky and it's basic. It's basic and bulky. And so we come down to this side, basic, bulky, E2 only. That's all that's going to happen. We cannot have SN2. So E2 only. Remember that for E2, our leaving group is attached to the alpha carbon, and so we look at our beta carbons to determine which hydrogens are going to be removed, and so we can have a double bond here, here, or here. And because this is a methyl and this is a methyl, that's going to be a repeat of a product. And so we're just going to have it to one of them, or we can have the double bond here. If you are unsure, just number. That can be very helpful in these problems. So this is 1, 2, 3, 4, 5. Make sure your problem has all 5 carbons. 1, 2, 3, 4, and 5. So this is the double bond between carbons 2 and 5. And this is the double bonds between carbon 2 and 3, and 5 is still attached to carbon 2 here. Okay, so we have those two products, and the problem asks us to draw the major product only. So the major product is always the most substituted product, which is this. So this is our most substituted product. And then in the middle, we kind of have an interesting problem where we have to figure out how to synthesize the alkyne, and then we're going to do 2 different reactions of the alkyne. So I'm going to put this in the middle of the slide. And so we have our alkyne here. And we need to synthesize that using NaNH2, 2 equivalents, and NH3. And this question mark means what substrate do you use? And then we're going to react this with lithium or sodium. And then we have an amine solvent, and then cold temperatures. And so this is our amine in the metal. This is the dissolving metal. Remember that dissolving metal conditions are going to give a trans-alkene. And then over on this side, we use H2, palladium, calcium carbonate, and quinoline. And this is going to give the cis-alkene. Just to make sure you get the backbone correct on these molecules, number. And so I have 6 carbons, and so my alkene, when I reduce in both of these cases, my alkene has to be between carbon 2 and 3. And so in this case it's trans, and trans is going to be part of your zigzag, and that is the easiest one to do. And so remember it's between carbons 2 and 3, so we're reducing from alkyne to trans-alkene. And then on this side we're reducing to a cis-alkene, and a cis-alkene is not as easy to draw, and so I usually start with the alkene first. And so my alkene is between carbons 2 and 3, and so I need carbon 1 to be cis with these remaining carbons. So we have 1, 2, 3, 4, 5, 6. And you should be able to name both of those. And then we also have to determine what's our starting material to give the alkyne. And so when we see these conditions, remember that this was called sodium amide. We do a long A to distinguish it from amide. So sodium amide, 2 equivalents. This was our double E2 reaction. And the starting material for an alkyne is a vicinal dihalide, and the halogens have to be at these 2 carbons to give the alkyne between them. And so we start with our 6 carbon chain, and then at carbons 2 and 3 we have our halogens. And so if we number again, if you're between carbons, if your halogens need to be at carbon 2 and 3 to get your alkyne between carbon 2 and 3, and this was called a vicinal dihalide. Okay. So this nicely summarizes the reactions we learned how to form an alkyne, and then reactions of alkyne, and there's one more that's not part of this problem. And remember that if you use H2 and palladium without the poisoned Lindlar's catalyst, then what happens in this case is you reduce all the way to the alkane, and you can go straight to the zigzag for the alkane of your 6 carbons.